Quantum reality bending. Imagine a rule book for reality. It's thick, ancient, and written in the language of mathematics. It contains the fundamental laws of physics that govern everything. Gravity pulls you down. You can't walk through a solid wall. An object cannot be in two places at once. These rules are absolute, non-negotiable. They provide the predictable, stable foundation for our entire existence. But what if I told you that deep within this cosmic rule book, hidden in the fine print, there's a clause, a loophole, a secret back door? A back door used constantly by the universe's smallest inhabitants to defy our reality, to treat the most fundamental laws as mere suggestions. This isn't a hypothetical scenario. It is the bedrock of the world we live in, a world far stranger than our senses let on. Our journey into this bizarre realm begins with a phenomenon so counterintuitive it sounds like something out of a comic book: quantum tunneling. Let's start with a simple classical picture. Imagine you have a rubber ball and you want to get it over a tall hill. You need to give it enough energy, a hard enough push, to get it to the top. If you don't give it enough energy, it will roll part way up and then roll back down. Every single time. There is a 0% chance it will magically appear on the other side. This is governed by the law of conservation of energy, a cornerstone of classical physics. The hill represents an energy barrier, and the ball, a particle, simply cannot overcome it without the required energy. It's an impassable wall. Now, let's shrink down to the quantum level, the world of electrons, protons, and other subatomic particles. Here, the rules change dramatically. That same particle, faced with that same energy barrier it doesn't have enough energy to overcome, can do something impossible. It can simply vanish from one side of the barrier and reappear on the other side, as if it had tunneled straight through the solid obstruction. It didn't break the barrier, it didn't go over it, it performed a kind of teleportation, ghosting through a region of space that should have been forbidden to it. This is quantum tunneling. It's the universe's secret back door in its most blatant form. How is this even possible? The answer lies in one of the most fundamental shifts in understanding reality: wave-particle duality. In the quantum world, a particle isn't just a tiny solid ball. It's also a wave of probability. Think of it this way. You can't say for certain where an electron is. You can only describe a region of space where it is. The Schrödinger equation, the master equation of quantum mechanics, describes this probability wave. When this wave encounters a barrier, most of it gets reflected, just like our rubber ball rolling back down the hill. But the wave doesn't just stop dead at the barrier. A tiny, faint part of that probability wave leaks through to the other side. And because the wave represents the probability of finding the particle, this tiny leak means there is a small, but very real, non-zero chance that the particle will be detected on the far side of the wall. It didn't travel through in the classical sense. Its existence is smeared out as a wave of potential, and some of that potential materializes on the other side. This isn't just a quirky theoretical footnote. It is a fundamental process that makes life itself possible. Look up at the sky. The sun, that colossal engine of creation, is powered by quantum tunneling. Inside its core, immense pressure forces hydrogen nuclei, which are just protons, incredibly close together. However, these protons are all positively charged, and like magnets, they repel each other with ferocious strength. According to classical physics, the temperatures and pressures in the sun's core, while extreme, are not high enough to give these protons the energy they need to overcome that electrostatic repulsion and fuse together. The sun shouldn't be on, but it is. The reason? The protons are tunneling through the energy barrier that separates them. They are using the universe's backdoor to initiate nuclear fusion, releasing the energy that warms our planet and allows life to flourish. Without quantum tunneling, the stars would not shine, and we would not be here to wonder about it. This reality-bending law isn't just happening in distant stars, it's in the technology you use every day. The flash memory in your smartphone or your computer's solid-state drive relies on this principle. Data is stored by trapping electrons in a floating gate, a tiny silicon chamber surrounded by an insulating layer, a barrier. To write or erase data, electrons are forced to tunnel through that non-conductive layer, an act that would be impossible under classical rules. Even our ability to see the building blocks of matter is thanks to this. The scanning tunneling microscope, an invention that allows us to image individual atoms, works by positioning an incredibly fine needle just above a surface. A voltage is applied, and electrons tunnel across the empty gap between the needle's tip and the surface. By measuring the flow of these tunneling electrons, the microscope can map out the atomic landscape with breathtaking precision. The back door of tunneling is just one of many. The quantum world is filled with these violations of common sense. Consider superposition, the idea that a particle can exist in multiple states or multiple locations at the very same time. It's not in place A, place B, it's in a probabilistic combination of A, B simultaneously. It only chooses a single definite state when we interact with it, when we measure it. Before that moment of observation, its reality is a ghostly haze of all possibilities. The solid, predictable world we perceive is just a facade, a high-level approximation of the seething, probabilistic, and utterly bizarre quantum chaos that lies beneath. The rules we thought were absolute are merely the emergent behavior of a much deeper, stranger set of laws, the forbidden laws that grant particles access to the universe's secret back door. Forbidden law implications. So, if particles can ghost through solid walls and exist in a haze of multiple realities at once, what kind of cosmic constitution allows for this? It's tempting to think of it as chaos, a glitch in the matrix. But it's the exact opposite. This behavior is governed by a set of rules so precise and so powerful, they make the classical laws of physics look like child's play. This is the forbidden law we've been talking about, and it's time to delve deeper into its profound and reality-shattering implications. The master key that unlocks this entire domain is the concept we touched upon earlier, wave-particle duality. Asking if an electron is a particle or a wave is like asking if water is for swimming or for drinking. It's both. Its nature depends on what you are doing with it. Nowhere is this more brilliantly demonstrated than in the most famous and mind-bending experiment in all of science, the double-slit experiment. The setup is simple. You fire tiny bits of matter, like electrons, one by one at a screen containing two thin parallel slits. Behind this screen is a detector that records where each electron lands. If electrons were just tiny baseballs, you'd expect to see two distinct bands on the detector, corresponding to the electrons that went through either the left slit or the right slit. Simple. But that's not what happens. What appears on the detector is a classic interference pattern, a series of multiple bands of high and low intensity. This is the telltale signature of waves. It's the same pattern you'd get if you sent water waves through the two slits. The waves would interfere with each other, creating peaks and troughs. This result means that each electron somehow passes through both slits simultaneously, as a wave of possibility, interfering with itself before hitting the detector as a single particle. But here is where it gets truly weird. The physicists, baffled, decided to watch. They placed a tiny detector at the slits to see which one each electron actually went through. As soon as they did this, as soon as they observed the particle's path, the interference pattern vanished completely. The electrons started behaving like well-behaved baseballs again, creating just two simple bands on the detector. The very act of measuring, of which path the particle took, forced it to choose a single reality. It's as if the universe holds its breath, maintaining a ghostly state of all possibilities, and only solidifies into a single, concrete reality when we look at it. This observer effect is a central mystery. It tells us that the forbidden law is not deterministic, but probabilistic. The universe, at its core, does not deal in certainties. It deals in odds. This leads us to the most spooky and profound implication of all: quantum entanglement. Imagine you create a pair of particles in such a way that their fates are linked. For example, their spin must be opposite. One will be spin up, and the other will be spin down. The catch is, until you measure them, neither particle has a definite spin. They both exist in a superposition of up and down. Now you separate these two particles. You could send one to the other side of the room or to the other side of the galaxy. The moment you measure the spin of your particle and find its spin up, you know instantly with absolute certainty that the other particle, light years away, has just become spin down. This connection is instantaneous, seemingly violating the speed of light, which Einstein believed was the ultimate speed limit of the universe. He famously derided this as spooky action at a distance. He was certain quantum mechanics was incomplete. Yet, decades of rigorous experiments have proven that this spooky connection is very real. The particles are not two separate things. They are a single, unified quantum system, no matter how far apart they are. These bizarre principles aren't just philosophical curiosities. They are the blueprints for a technological revolution. This is the foundation of quantum computing. A classical computer uses bits, which can be either a 0 or a 1. A quantum computer uses quantum qubits. Thanks to superposition, a qubit can be a 0, a 1, or both at the same time. By linking qubits together through entanglement, an array of qubits can explore millions of possibilities simultaneously. This parallel processing power will allow us to solve problems that are impossible for even the most powerful supercomputers today, from designing revolutionary new medicines and materials to creating hyper-intelligent AI. Entanglement also promises unhackable communication. If you use entangled particles to generate a cryptographic key, any attempt by an eavesdropper to intercept and measure a particle would instantly break the entanglement, alerting the legitimate users that their security has been compromised. Ultimately, these laws force us to question the very nature of reality itself. If the universe only settles on a definite state when observed, what does that say about the role of consciousness? If two particles can be intrinsically linked across the cosmos, does it suggest a deeper, holistic interconnectedness to everything? The universe's secret back door isn't a glitch. It's the main entrance. It reveals that the solid, predictable world we experience is just a thin veneer, a large-scale illusion born from a bubbling, probabilistic quantum realm that is far more mysterious than we ever imagined. The forbidden laws of quantum mechanics are not forbidden at all. They are the true, fundamental operating system of our cosmos. The real question is, what other profound rules are we just beginning to uncover?